So this, I'm going to talk about models. Just realised that the chap on that video had a very strong accent, so I'm doing my best to try and speak in a much clearer way than he did. Apologise for that in advance. So the ecological modelling that's taking part in the books has covered a very broad range of ecosystem components, and a massive number of man-hours have gone into this. I won't be going through it all because one of our single deliverables ended up being about 296 pages long. So in the spirit of the Pikachu, we'll try and keep it brief. So I thought instead I'd try and put a bit of context into the modelling that my colleagues have been doing mostly. Keep it simple. Model is anything used in any way to represent anything else. You got that? It's going to get more difficult. So there is no mystery to modelling. Modelling is not some kind of occult practice. In fact, we all model continuously. It's called perception. So as I'm speaking to you now, and as you're observing a picture of the brain, that picture is actually represented at the back of your head in some cells. So you can think about that at a minute. Where does this picture exist? It actually exists in the back of your head. It doesn't exist there, as far as you're concerned. I'm looking a bit concerned where we're going with this. So, from the information that comes through your eyeballs, you recreate reality. So you're modeling right now, you're representing some kind of abstract concept of chemical signals as some kind of reality. And that's all modeling is. You take some inputs, you process them using rules, models, and frameworks, and then you have some kind of understanding of what that means, and then you take action based on that understanding. And we do this as individual humans every day, every second of every day. Sounds easy. So what are the things that kind of define the process of modelling? It's really the concept of trying to make things simpler, so trying to take all the complexities of what we're presented with and focus down on what are the key issues. So the entire idea of modelling is actually something that happens inside of us. It's done for our benefit, so we can understand the concepts. So to do that, you have to sacrifice something. You can't have a map of the world at the same resolution as the world, because then you've just got the world. So we have to tell me if I'm going too quick. So we have to do some kind of simplification and some kind of process to achieve this. Turns out that this has become more possible, or the things that we've been able to tackle have become more possible with the increase in computing power. So the models that we construct in our brain are one kind of model, and then the model that we input into a computer to get calculated is another kind of model. And the complexity and the structure of those models are dependent on the system that we use to create them. So ecological modeling isn't special. It does happen typically on computers. Why have we seemed to have so much modeling, perhaps, you could ask? Well, there is a reason. It's not just because we've got nice computers and we have to use them for something. You could put it in the context of an increased concern with rates of change in nature and trying to understand the impact of humanity on nature. So there's been discussion in the geological community that we have now entered the Anthropocene. So we have decided, or are proposing at least, that the time that we exist in now is demonstrably different from every geological era that has happened before, and the agent that has caused that change is mankind. So are there changes in the environment that are happening more rapidly? Are there processes which are interacting at scales which they wouldn't previously have interacted in? And are we responsible for those? So you can have whatever opinion you like on that, but people want to know. So for example, you could imagine discard bans. or removing discard bands, you have a major perturbation in the system that would never happen in nature. And does the rate of change of that perturbation have an effect on the system? So these are the kinds of questions you could maybe start to think of. Why would we be looking at modeling these systems? So I'm not a biologist, and I understand that people have different opinions on the validity or the value of different kinds of approaches to looking at systems. And you may think there's a philosophical problem with modeling biological systems. It seems that most biological philosophers say that biology is autonomous from physical science. It's quite an issue if you think about it. So maybe there is something fundamentally different about biology that we shouldn't try and quantify it. Certainly some people have written some interesting articles about the nature of modeling. It's a contentious issue. And some people think it's more about capturing our own inadequacies than actually representing nature. So is that the case? Well, certainly the modelers and devotes don't think so. Modelers and devotes think that they have a very useful contribution. So I've made some statements about the role that modeling can play, and as you can see, there's many articles that you can go to from the devotes modeling community and check them out yourselves. But they are large claims to make about large systems and systems with great degrees of complexity. So it is worth thinking what we're doing whenever we're creating these models. So there are certain aspects of models that we have to make trade-offs the whole time. So the central sentence there is that the simulations make creative use of calculation techniques that can only be motivated extra mathematically and extra theoretically. So that's really telling you that you have to think about and come up with a logical system to your modeling. You can't expect that because you can put some numbers into a computer and get some numbers out, that has any particular meaning. So the skill in modeling maybe isn't necessarily in the complexity, but in the logic behind it. So a nice way for me to think about the modeling is that Richard Evans had some nice insights as to what could be achieved. And his opinion was that you could get 2 out of 3 of these particular aspects. So you couldn't have your cake and eat it. You can't have everything in one model. You have to decide what you're going to aim for and realize that you're not capturing everything in one go. So generality or transferability gives you insight into laws and mechanisms. Precision helps you quantify, and with accuracy you can approximate reality. So that's what we're kind of trying to get for. Those key things are what we're after, but there are barriers. So some of the barriers that we face continually are contingency, so things being true only in a restricted sense. So we can create models for local systems that work, but if we applied the same rules that we learned in those local systems to the broader ecosystems, they would fail. With precision, we are always forced to aggregate. We have to simplify the system, and that obviously reduces accuracy or the precision. And with accuracy, we have to abstract. We have to try and pull things together and make simplified versions of the objects we're modeling. So these are the hindrances. In devotes, there's a very extensive process of scoping before the modeling took place, so to check out what exists. And this, I think, is fantastically useful to get an overview of all the modeling activity that is going on in Europe. This is broken down by sea areas, so it gets more detail. So you can go in and find out exactly what kind of modeling is happening in what areas, and they also break it down into what indicators or what pressures are being looked at. So this is useful as a background to the modelling activity. And then with the modelling that happens in devotes, it starts to ask really interesting questions about the spatial distribution of various ecosystem indicators. Can we use one indicator for an entire area? Do we have to split the area up? What is the most valid way of splitting an area up? Do all the indicators vary synchronously in our study areas, or are they out of phase? Are there similar magnitudes of variation, or do the magnitudes vary as well? So these are the kind of things that give you a much better set of questions to ask of what you want from an indicator and from an ecosystem. The other reason why we need models is because it's very complicated. This is the interaction, and this is a simplification, of course, but the interactions and the kinds of networks that exist in nature are beyond what we can reliably understand through our own mental processes. So we can create these interacting food networks, and we can also look at sensitivities. So with our existing data, how sensitive is that to small alterations in the initial conditions? That's that tiny little box in the bottom. So in summary, modelling is a process that isn't mystical, it's not magical, and it does have to be a process of refinement. So each model gives better questions for the next model, and each set of questions then lets you tune and refine your modelling activity, and that provides feedback for what you're going to do next, so you get a better model because your previous model has told you something. Thank you, and thank you to all the efforts.